Hello everyone, I'm Erin Elliott. I'm an engineer here at ZMAX. I'm here to talk about the contrast loss map that we have added to OpticStudio. The contrast loss map is designed to work with our contrast merit function. If I look in the merit function editor at the optimization wizard, we have this new option for a contrast optimization, and we can specify the spatial frequency. This optimizes the MTF at the designated spatial frequency. And it does that by adding these operands that calculate the difference between a shifted and an unshifted wavefront in the pupil. The contrast loss map is meant to give us a visual of this optimization process. You can find it here under Analyze, MTF, Contrast Loss, way at the bottom. If I open that, you can see that I can select a sampling and a frequency. This is the frequency of the MTF that you care about. I'll just do this for wavelength in field 1 for now. And that sampling looks a little low, so let me bump it up a little. Okay, so this plot is telling me where in the pupil the wavefront is causing the most loss in the MTF. And you can see on the plot on the left, the most loss is coming from the left and right sides of the pupil. And for the tangential, where the pupil is shifted upward, the most MTF loss is coming from the top and the bottom of the pupil. So let's look at a particular system to see how this works. Here I just have a spherical singlet that I'm using at its 2 F points, and this system will have a lot of residual spherical aberration in it. The wavefront map tells us that we've got about 1.3 waves peak to valley, and the contrast loss plot that goes with that looks like this. If I imagine shifting the pupil slightly to the right and then calculating the difference between the OPD, you can see why the magnitude of these circles is larger, because that difference is larger and has more of an effect on the MTF. Just to look at the equations that we're plotting, the size of the circles here is this equation. It's the difference in the OPD times 2 pi to convert it to an angle. It's 1 minus the cosine of that determines the size of this circle, and we divide by a half so that the range of the plot can go from -1 to 1. The clock dial in the plot is just 2 pi times the OPD of the wavefront. With a little bit of practice, we think that we can use the clock dial to see the underlying shape of the underlying wavefront. Okay, so the magnitude of the circles tells us where we're losing MTF, and the clock dial just tells us the underlying shape of the wavefront. If I switch now to a slightly faster system that has, again, using it at the 2 F points, but now I have 4.3 waves of spherical. If I create a contrast loss plot for that with a higher sampling, you will see that the patterns here start to look like shear plate interferograms. That's because we're essentially plotting an interferogram of the wavefront difference, or of the wavefront slope. You can see that in this case, we're getting the most loss of MTF along this band here at half a wave of OPD difference between the shifted and the unshifted pupil functions. So that, in a nutshell, is the contrast loss plot. We think that we'll be able to use it to see where in the pupil we are losing contrast in the MTF.